So you probably remember from last year that a matrix is nothing more than an array, a rectangular array of numbers. We like to talk about matrices in terms of their dimensions, and their dimensions are based on how many rows they have versus how many columns they have. So when you're trying to remember which is a row and which is a column, think of Greek architecture. They had lots of columns, right? Those columns went up and down. The rows are going side to side. So when we look at this first matrix, it has 2 rows and 3 columns. So it is called a 2 by 3 matrix, and we call that its order. The order of this matrix is 2 by 3. Bless you. A square matrix has the same number of rows as columns. So the second example is a 3 by 3 square matrix because it has 3 rows and 3 columns. So on your sheet you have 3 or 4 examples of matrices. I'd like you to figure out what the order of each of those matrices are. What each of them is. All right, Emery, what's the order of the first matrix? Letter A. So how many rows and how many columns does it have? It's a 2 by 2. 2 rows, 2 columns. It's a 2 by 2. That's its order. It's dimensions. Okay. Holly, what's the second one? What does it have for an order? By 1. 1 row by 1 column. There's only one element there. Okay. Nicole, what would be the third one? Very good. And Jackson, what is the fourth one? 3 by 1. Make sense? Some of your first problems that you're doing for your assignment are as simple as that. Okay? All right, so there are times that we want to use matrices to solve systems of equations. In fact, that's one of our main uses for it. And if you remember back to last chapter, when we were working with a 3 by 3, or not really a 3 by 3, but a system of 3 equations with 3 unknowns, then it would have been nice to be able to use another method. And that's what this chapter is kind of about, is how do we use matrices to do other things. So if you look at this system of equations, it has 1x minus 4y plus 3z equals 5 and so forth, right? Well, you can strip off the variables and just leave the coefficients along with the answer to that particular equation. So that's what's called an augmented matrix. An augmented matrix has no variables in it. We simply remove the coefficients or place the coefficients in the matrix along with the answer, and then we separate them with a dashed line to distinguish them from the coefficients. So if I ask you for an augmented matrix, I want you to strip all the variables off, put a dashed line, put your answers. If I ask you for a coefficient matrix, I want to know what are the coefficients of those variables. And if I would ask you for an answer matrix, I could ask you just for the 5, negative 3, 6 in a 3 by 1 matrix. That's an answer matrix. Questions so far? All right. This is just the answer matrix. If we have a coefficient matrix that only has the coefficients, then sometimes we want to have an answer matrix that just has the answers. Okay, and we'll use that later on. But I want you to be exposed to that topic or that idea, that term. All right, here we go. So next, we want to talk about, already done this, right? Elementary row operations. So when we were solving systems of equations, one of the things that we would do is we would say, hey, I need to make a particular variable disappear, right? So to make a particular variable disappear, if this was an augmented matrix, it would be 3x minus 4y equals 7, and x minus y equals 3. Make sense? Okay. So if I wanted to do something with this matrix, first of all, I can switch the order or with these equations, I can switch the order of the equations and it doesn't change anything, right? That makes sense? Okay, if I write this one first and this one second or vice versa, they're going to get the same result. Okay, that's our first thing. We can interchange two rows. So this row can go down here and this row can come to the top. Okay, that's one of our options. And it doesn't impact the answers. The second thing that we can do is we can replace any row by a non-zero multiple of itself. Our second rule for matrix operations. So if we wanted to make the x's go away here, what do we typically do? We multiply the bottom one by -3. As long as we multiplied every single term by -3, we're not impacting the equation itself, just its appearance, right? So the same thing happened here. Okay, they took every single term in this first row times a -3 and wrote the result. Make sense? Okay, so that's the second thing we can do. We can interchange rows, and we can multiply the same row by the same number, as long as it's the whole row. Okay, last thing. We can replace any row by the sum of itself and a multiple of any other row in the matrix. Okay, so we can add these two up. So we took that top row times a -3, adding it to the second row gives me a 0. When we took this top row times a -3, we got a +3, +3 and -4 gives me a -1. That top row times a -3 gave me a -9, -9 and 7 gives me a -2. Make sense? All right, so good question. In reality, we wouldn't want to keep this top row as a -3, 3, and 9, -9. It would be better as a +1, a -1, and a +3. Because, and I'll explain in just a second. Okay, so far so good. I'm going to show you the process or the reason for our madness. Okay, but you're okay with the fact that we can interchange rows, we can multiply the same thing by everybody without impacting our net result, and we can add two rows together. Okay, or the product of a number and a row with another row. Okay, so here's our method to our madness. Okay, and they're going to ask you in some of the earlier problems that you do to just do some elementary row operations. Okay, so we have a matrix here, and it's an augmented matrix, and they asked us, hey, we want to make an x go away. Okay, the coefficient for x is going to go away. So if we have 1x minus 4y plus 3z, a -1x plus 3y minus z, and a 2x plus 0 minus 4z, can we add these up and make the 0 or make the 1 go away? The -1? Okay, so they're going to ask you to do things like take row 1, add row 2, and place that into row 2 spot. Okay, so Julia, if I take 1 and -1 and add them up, what do I get? And -4 and 3, and 3 and -1, and finally 5 and -3. And so far that's looking better already. Okay. Now, it would be kind of nice if we could make this x go away as well. Make sense? What would we have to do to make this 2 become a 0? Exactly. Multiply row 1 times negative 2, and then add it to row 3, and place it into row 3. Okay? So let's do that. So if we take negative 2 times 1, what do we get, Lauren? Plus 2. Negative 2 times negative 4, 8 plus 0. Negative 2 times 3, plus a negative 4. And negative 2 times 5, plus 6. Make sense? Maybe, or at least you understand, you see what we're doing. Okay, may not make sense yet. So far, so good? Okay, and then our other things could potentially stay the same. All right, so next example then, or next slide, shows you the method to our madness. Okay? So we have something called row-echelon form, and we have something called reduced row-echelon form. You want to find that part on your notes? So we want to notice what's different or what's unique to these that we haven't seen in the matrices that we've seen so far. So what do you notice about the row-echelon form? There's a line of ones. That line of ones is called our main diagonal. So the main diagonal is all ones. What else do you notice about the row-echelon form? Good. Anything below the main diagonal is zeros. How does that compare to reduced row-echelon form? So the main diagonal is still ones, but every one in the coefficient portion of the matrix, is the rest of them are zeros, right? So the main diagonal is all ones. Has all ones. And the rest of the main rest of those are zeros. Okay, so now let's show the difference between the two. Okay, let's think about what this one would say back if we had variables in it. Okay, does everyone see that we have a lovely bottom row that says z equals 2? Okay, the middle row says y minus 2z equals negative 2. So could we back substitute and figure out what y is? We substitute a 2 in for z, we'll have a negative 4. And so we would add 4 to both sides, and y becomes 2. And our third equation is x minus 4y plus 3z is 5. So could we substitute 2 and 2 in for y and z and figure out what x is? Okay, so x minus 2 times 2 plus 3 times 2 will be 5. So a negative 2 going to the other side becomes 7. So we could write our ordered triple as 7, 2, 2. Back substitution in echelon form. Make sense? Okay. What do you notice about reduced row echelon form? We can look at this one and see the answers, can't we? Because there are no y's and z's here. It's just x equals 7, y equals 2, z equals 2. Make sense? Okay. So we're going to practice this to make sure that we can get them into either row echelon form or reduced row echelon form as a method for solving systems of equations. Make sense? Okay, so here comes our last example. So we're in the bottom part of your paper. And you'll have to kind of write it small. Although we have the back, so we can always flip over to the back if we need to. Okay, so I want you to start by writing that as an augmented matrix. So far, so good? All right. Now, where would we begin? If we were trying to make x's and y's go away, what's the easiest one to try to eliminate? Potentially from the start. X. Absolutely. What happens when we add the second and the third row together? We'll just have z. So where do we want to put it? Put our answer in the third row, right? In order to make it look like this, we want to have it in the third row. Okay? So we're going to add row 2 plus row 3 and place it in row 3. Now, if you write these things down, that helps me understand what you were trying to do, so I can help figure out where you made a mistake if you do, because of course they're going to trickle all the way through it. I'm going to do this so that you can see what in the heck I did, right? So that you understand the process. All right, so Vincent, when I add row 2 plus row 3, what am I going to get? Make sense? Okay, and again, if you don't do the little dash dots, you don't have to. I've seen it both ways. Our textbook shows it. Okay. All right, so that looks good. Now, to save on paper, maybe we can do something else without rewriting the first 2 rows again. Okay. So, what's something else that we could do? What could eliminate this -1? Multiply it by 3 and add it to row 1, right? Okay. So we're going to take row 2 times 3 and add it to row, add it to row 1, and we're going to put it in row 2. I want to try to get rid of that number there. Now, if you can't mentally do that, need to put a little row up above, you can do that. But let's think about what this is. 3 times negative 1 plus 3. 3 times 1 plus negative 2. 3 times 2. 6 plus 1. 3 times negative 10. Negative 30 and a positive 15. So far, so good. Let's rewrite that top row. All right, looking at that, do we know what z is? What is it? Negative 2, right? How did you know that? Divided everybody by negative 2, right? So we're going to take row 3 and divide it by negative 2, or times a negative 1/2. Purists in matrix theory would say we don't divide, we multiply by the fraction. And then we're going to place that into row 3. So think about it as dividing by negative 2. 0, 0, 1, negative 2. Puts us in a great place, right? Which row would we want to use to get rid of or make this negative 2 become 0? What could we add to negative 2 to get a 0? 2. So which one has something that we can work with to make a 2? Row 2, right? And the beauty of having a 0 here is what happens when you take 2 times 0. And when you add that to 3, it doesn't change it, does it? It doesn't make it any bigger or change it. So let's take row 2 times 2 and add it to row 1. Okay, plus 2. All right, so Paige, if I take 0 times 2, I get plus 3. 1 times 2 plus a negative 2. 7 times 2 plus 1. And finally, negative 15 times 2 plus 15. Excellent. Liking that? Because if we can get, now we could have just stopped at row echelon form, right, to get this in row echelon. So if we're doing that, the only thing that we would have to do is get a 1 here, which we have, and we could stop. Okay, but I want to show you how to get it all the way to reduced row echelon form, so we don't have to do the back substitution. So our goal then is to say, hey, I want to have a 0 here, and here, and here. Okay, so we're looking for a way to make this into a 0. And the nice thing is a lot of times once these things become zeros, then we can divide, and we end up with a 1. Does that make sense? Okay, we're going to try to give you numbers that are nice numbers, so you aren't usually going to have fractions for your answers. They're hard enough the way it is. Make sense? Okay, so we have, if we're trying to make it in reduced row echelon form, a 7 to get rid of as well. So what are we going to add to this 7 to make it go away? And where can we get a negative 7 at? Bottom row, right? Okay, because it has lots of zeros, and 0 times negative 7 doesn't impact anything as far as adding extra numbers to it. Yes, sir? It's 2 rows, but it'll be 3 in just a moment. We're just trying to save paper. Okay, so if you want to build a new matrix every time and just do 1, you sure can do that. I'm just trying to save some paper since you don't have a lot of space on your notes sheet. Okay, So goal here, we're going to take this row 3 times 7 and add it to row 2. Okay, so Fletcher, help me out. If I take 0 times 7, I get plus 0. 0 times 7 plus 1. 0 times, or I'm sorry, 1 times 7, negative 7. Not positive 7, negative 7. So 1 times negative 7 plus 7. Negative 2 times a negative 7 plus a negative 15. Okay. Now we've got our 3 rows back. All right. Looks like we just need to do a couple things, right? What's the next thing we'd likely do? Multiply the top row by 1/3. If you're a matrix purist, you're going to say we only multiply, not divide. So if we take row 1 times 1/3, we're going to get 1, 0, 5, and negative 5, right? All I did was copy the other 2 rows. What's the last thing we need to do to make this in reduced row echelon form? Row 3 times negative 5 added to row 1. So 1 plus 0 and 0 plus 0, but 5 plus a negative 5 and negative 5 plus negative or positive 10. Right? So if we take everybody times negative 5, positive 10 and negative 5 is, and now we have our result in reduced row echelon form. So what is x? What is y? And what is z? Yes, sir. It's in the x. So remember, this is our, now if we took it back and wrote it into non-reduced row echelon, right? Or put it back into our equation form, 1x plus 0y plus 0z is 5. So x equals 5. Y equals negative 1. And z is a negative 2. Make sense? All right. Assignment. The first ones are things, easy things like tell me what's the order and tell me how to, if I do this, if I swap these 2 rows, what's it going to look like? Or if I multiply this one by something and add it to something, what will I get?